Welcome back. In previous segments, we have determined whether a particular big O relationship is true or false. Now in this segment, we're going to tackle a slightly different problem, which is, given a function, can we find a good upper bound for it? Now, what do we mean by a good upper bound? Well, it's time to remember that we're going to use the concept of a big O relationship to study the runtime or the time complexity of an algorithm. So in particular, one of our goals will be, given a runtime function f of n, we will want to find an upper bound for f of n. In other words, a function g of n such that f of n is big O of g of n. We want to make sure the runtime algorithm does not grow any faster than a particular function. And our goal will be to find such a function. Now, of course, if we determine that f of n is, for example, big O of n squared, it is also true that f of n is big O of n cubed, and n to the power 4, and n to the power 100. And even it's big O of 2 to the power n, or big O of n factorial, because all of these functions grow faster than n squared. But notice, we have a lot more information in the fact that f of n is big O of n squared than we do in all of the other cases, because n squared then is a better approximation for the runtime of the algorithm under consideration. So the conclusion of this little discussion here is that we're not just interested in any function g of n. We're interested in finding an upper bound for f of n, namely a function g of n, but that function should be as small as possible. In particular, its rate of growth should be as low as possible, so as to be a better approximation of the rate of growth of f of n. Now let's consider our first example of a function f of n for which we're interested in finding the best upper bound. In other words, the smallest function g of n that's an upper bound for f of n. To answer this question, we're going to use all of the facts and theorems that we discussed in previous segments. So the function f of n we're considering here is the sum of two functions. The first function is itself a product of n plus 1 and the function log of n squared plus 1. The second component in the addition is 3 times n squared. So to determine the big O upper bound that most closely approximates the function f of n, we're going to proceed from left to right by considering the components of f of n one by one. First, we're going to look at the function n plus 1. This function is a polynomial of degree 1, so we know it's big O of n. Let's record that. Now the second function, log of n squared plus 1, is not really a reference function. So we need to do a little bit more work to find an upper bound for it. So first, let's consider the inside function n squared plus 1. Well, clearly n squared is less than or equal to itself, and 1 is less than or equal to n squared, where n is greater than 1. Therefore, n squared plus 1 is less than or equal to n squared plus n squared, or 2n squared, as long as n is large enough. Now, having established this inequality, we can apply the logarithm to both sides of the inequality while preserving the inequality, because the logarithm function is a strictly increasing function. So the next inference is that the log base 2 of n squared plus 1 is less than or equal to the log base 2 of 2 times n squared. Notice this is the function that we are interested in finding an upper bound for, and now we can work and we write this function as follows. Based on the definition of the logarithmic function, log of n squared plus n squared, or 2 times n squared here, is equal to log of 2 plus 2 times log n. That's because, remember, the logarithm of a product is the sum of the logarithms. And again, the logarithm of n squared, which is n times n, is the same as log n plus log n, or 2 times log n. So clearly, this expression is equal to that one. If you have trouble with this, make sure you review the video on the logarithmic functions. Now we need to find an upper bound for this expression, which fortunately is not too hard. Notice that log of 2 is less than or equal to log n if n is greater than 2. In other words, log 2 is less than or equal to log n when n is large enough, and of course 2 log n is less than or equal to 2 log n. So when you add those two expressions, we can use theorem 1 or one of its corollaries to infer that this expression is less than or equal to log n plus 2 log n, or 3 log n, as long, again, as n is greater than 2, which was the condition to upper bound log of 2. So in conclusion, we prove that this function is less than or equal to 3 times log n, where 3 is a constant and n is greater than k. That's a standard definition of a big O relationship, assuming all the numbers are positive. So in conclusion, log of n squared plus 1 is big O of log n. Let's record that up here in our definition of f of n. Next, we can use theorem 2 again to upper bound the product of this function f1 with this function f2, which are respectively upper bounded by g1 and g2. So step 3 simply infers that n plus 1 times the log of n squared plus 1 is upper bounded by the product of n and log n. In other words, this function is big O of n log n. Now that we have an upper bound for the first component of f of n, we can consider the second component of the addition. The function 3 times n squared, being a polynomial of degree 2, is clearly big O of n squared. Let's record that. And finally, we can use theorem 1 pertaining to additions of functions to infer that f of n is big O of the maximum of this function with this function. Of course, you remember that n squared grows faster than n log n. In other words, this term of f of n dominates the first one. So in conclusion, f of n is big O of n squared. And this concludes our example.